Okay, I want to give a quick motivation for using or for developing comparison tests, right? Let's look at this first. So I've got three examples. Here's the first one in purple, and then here's one in blue, and then here's one in red. Okay, so for the first example, I don't know if you can notice or if you can tell, but this one on the left, we can actually, this would be good for the integral test because, first of all, if we think about f of x, which is x over x squared plus 3 squared, it is, it's going to be positive, it's going to be decreasing, it's going to be continuous, and we can apply the integral test, and then we can integrate x over x squared plus 3 quantity squared dx from 1 to infinity. We can totally integrate this and see if it converges or diverges, right? So this first series is good for the integral test. The second series, not so good. Even though these series only differ by a factor of n, right? So even though these series are very, very close to each other and very similar, the first one is good for the integral test. The second one is not so good. Okay, let's look at this second example here. Now, the first integral, the first series is good for what? What would be a test that we use to determine if it converges or diverges? You got it. We would want to use the geometric series test because this is a geometric series, right? We also actually could use the nth term divergence test, but this is a geometric series with our ratio 3 over 2. Over here, right on the right-hand side, we've got another series, which is very similar to a geometric series, but we can't use the geometric series test because we have this factor of n in front. Okay, and then let's look at our last example here. What would be a good test? Geometric series? Nope. But we would want to use the p-series test. And in fact, we have a p-series with p equals 3, so we can look at this on the left and determine that it converges, right? Because p is greater than 1. But on the right-hand side, again, even though it's so close to 1 over n cubed, we can't use a p-series test. It's not a p-series. We can't even use, for this one on the right, we can't even use the integral test because we wouldn't be able to integrate 1 over x cubed plus 1 dx, right? So even though series are,
It's 18 hours.
thank you, even though series look very similar to each other, this is a problem, and we'd love to be able to use the fact that, say, this series is very similar to that series, and then use that somehow to determine the convergence of our, of this unknown series. That's why we want to have comparison tests. Now, just as a quick little bonus, what I want to do is I want to share with you how to use Wolfram, and we can use Wolfram Alpha, or you can use Mathematica, whatever you are familiar with. I'm just going to go here to Wolfram Alpha. Please know that we can have Wolfram Alpha for free, actually. So you can download that, and I posted the link on Slack. So I'm just going to go to a sandbox because I don't have Mathematica downloaded um, on my computer. But actually, I'll just go back to Wolfram Alpha and make life a little easier. Okay, so if I go to Wolfram Alpha, and I'm going to plug in, here I'm just going to put in sum. And now what was the sum I was looking at? I think it was n divided by, and then it was n squared, where's my squared? N squared plus 3, and then that quantity squared. Okay, go. So I hit enter. Here's the results. The results are the input interpretation is showing me is this, it's showing me what I input, and this is correct, right? And it's already telling me about the convergence test. We'll learn about the ratio test a little bit later on, but notice it says by the comparison test, the series converges. Wolfram Alpha is using a comparison test, okay? It gives you a formula for the partial sum, right? Now this formula is actually very complicated, and that the notation, this function here is psi, or not psi, I think gamma. So it's like a brand new function. It involves imaginary numbers, but if you need a formula for the partial sum, there it is. And then you can graph the partial sums. So notice here that why would you want to graph the partial sums? Because to determine if a series is convergent, you're looking to see if the limit of the partial sums exists. And it looks like this limit does exist. It looks like the partial sums are getting closer and closer to some number. And I could say, show more terms, right? So I could say, hey, show even more terms. I don't believe it, right? Do you see? Show even more terms, right? So you can see here that our partial sums truly are tending towards some number that's like a little bit above 0.15. So by the comparison test, the series converges. So feel free, and I encourage you to play around with Wolfram Alpha, with Mathematica. Use technology. That's the smartest thing to do, is to be able to use technology. Years from now, you will have forgotten, probably, you will have forgotten, how to do these series and, convergence or divergence. But if you know about Wolfram Alpha, then you can just pop onto Wolfram Alpha and remember, oh yeah, I can use, I can do this online. There's an online calculator. And again, I encourage you to play around with Mathematica. Download it if you can, and just figure out the commands. Play around with it a little bit. It is an invaluable source. Be smart. Be smart about how you're using it, right? Because again, you won't be able to use it on the exams, but you're doing homework. You want to check yourself. Sorry. You want to check yourself. That's exactly what Wolfram Alpha and Mathematica are for. All right.